There's something humbling about staring into the depths of space, knowing that every flicker of light is a story waiting to be told, a mystery begging to be unraveled. And among the countless galaxies stretching across the cosmos, one in particular stands out not just for its beauty, but for its strangeness, NGC 262. Imagine a place where the rules of physics seem to bend, where objects exist that challenge everything we think we know about the universe. This galaxy, swirling with secrets, is home to phenomena so bizarre they've left even the brightest astronomers scratching their heads. What if I told you that nestled within NGC 262 are objects so peculiar they defy explanation? We're not talking about ordinary stars or planets here, but structures and anomalies that shouldn't exist, yet somehow they do. Some glow with impossible colors, others move in ways that break the laws of motion, and a few even seem to vanish and reappear without warning. It's as if the galaxy itself is playing tricks on us, hiding clues to a puzzle we're only beginning to understand. And today, we're going to uncover 30 of these mind-bending enigmas, each one more astonishing than the last. This isn't just a tour of cosmic oddities, it's a journey into the unknown, a chance to peer into the edges of our understanding and ask the questions that keep scientists awake at night. What forces could create such strange objects? Are they natural, or could they hint at something far beyond our comprehension? As we explore these 30 mysteries, remember, every discovery, no matter how small, brings us one step closer to unraveling the grand story of the universe. So, buckle up. By the time we're done, you'll see NGC 262 in a whole new light, and maybe even question what's really possible out there in the vast, uncharted dark. The first strangeness awaiting us in NGC 262 is something straight out of a cosmic ghost story, the Phantom Nebula. Picture this, a vast, shimmering cloud of gas and dust that flickers in and out of existence, sometimes visible for years, then vanishing without a trace for decades. When it does appear, it glows with spectral colors unlike anything else in the galaxy, shades of violet and deep crimson that don't match the emissions of any known element. Astronomers have trained their most powerful telescopes on it, only to watch it dissolve like mist in sunlight, leaving behind more questions than answers. What makes this nebula so baffling isn't just its disappearing act. Its very structure defies the laws of physics as we understand them. Normally, nebulae are illuminated by nearby stars or the remnants of stellar explosions, but the Phantom Nebula emits light in chaotic bursts, as if powered by something far more exotic. Some scientists speculate it could be the leftover shockwave of a supernova so ancient, its original star has long since faded from memory. Others wonder if it's evidence of an entirely new cosmic phenomenon, a type of celestial object we've never encountered before. Then there's the eerie way it moves. Unlike ordinary nebulae which drift predictably through space, this one seems to dart and shift, almost as if it's reacting to unseen forces. Could invisible dark matter be tugging at it? Is it interacting with some hidden dimension? Theories abound, but one thing's certain: the Phantom Nebula refuses to fit neatly into any of our models. It's a cosmic rebel, daring us to rethink what we know about the life cycles of stars, the behavior of interstellar gas, and even the nature of reality itself. And just when researchers think they've caught it in a moment of stability, it slips away again, leaving behind only whispers of data and a tantalizing challenge. If we could just decode its secrets, we might unlock clues about how galaxies evolve, how matter behaves under extreme conditions, and whether the universe holds phenomena we haven't even dreamed of yet. The Phantom Nebula isn't just a mystery, it's a doorway, and on the other side could be revelations that rewrite astronomy itself. Now, let's turn our attention to something even more mind-bending: the twisting black hole. Picture a cosmic whirlpool so extreme that it doesn't just swallow light, it contorts it into impossible shapes. Unlike the neat, flat accretion disks we usually associate with black holes, this one looks like it's been crumpled by some unseen hand, spiraling inward at angles that defy logic. Light doesn't just bend around it, it spirals in chaotic loops, creating halos and mirages that shift unpredictably. Astronomers first noticed this anomaly when they spotted flickering X-rays blinking in and out of existence, as if the black hole itself were playing a cosmic game of hide and seek. What makes this object so strange isn't just its twisted appearance. According to everything we know about black holes, their accretion disks should align predictably with their spin. But this one, it wobbles. Imagine a spinning top that doesn't just slow down, it writhes as if something is tugging at it from the inside. Some researchers think the black hole might be rotating at near light speeds, warping spacetime so violently that the disk can't stabilize. Others speculate there could be an invisible companion, another black hole, or even a rogue neutron star, locked in a violent dance, their gravitational tug of war distorting the disk into this nightmare shape. Then there's the light. Normally, a black hole's gravity bends light predictably, creating the iconic Einstein rings we've all seen in simulations. But here, the light doesn't curve, it fragments. Some wavelengths get amplified while others vanish entirely, as if passing through an invisible cosmic prism. Could this be evidence of some exotic physics at play, quantum effects normally buried deep in theory? Or is the black hole feeding on something we've never seen before, a type of matter or energy that interacts with light in ways we can't yet model? The most unsettling part, this black hole doesn't just defy our models, it seems to change its behavior over time. Months of observations show the disk twisting further, then suddenly snapping back, as if something inside is constantly adjusting the rules. It's like watching a cosmic experiment unfold in real time, one where we don't know the variables or the outcome. If we can decipher what's happening here, it could rewrite our understanding of how black holes evolve, how they shape their galaxies, and even how spacetime itself behaves under the most extreme conditions. The twisting black hole isn't just a curiosity, it's a challenge, a puzzle that could unlock secrets about the very fabric of the universe. And yet, for all its strangeness, it might not be alone. Some astronomers are now scanning other galaxies for similar anomalies, wondering if this is a fluke, or the first glimpse of a whole new class of black holes we never knew existed. Every flicker, every warp in that disk is a clue, whispering that there's so much more to learn. And with each new observation, we edge closer to answers that might just upend everything we thought we knew. Deep within the swirling arms of NGC 262, an object glows with such precise geometry, it stops astronomers mid-sentence, the glowing hexagon. This colossal structure, spanning nearly half a light-year, pulses with radiation in a perfect six-sided pattern, its edges so sharply defined they look drawn by some cosmic architect. At first glance, you'd swear it was an optical illusion, a trick of light, or a flaw in the data. But repeated observations confirm it's real, and its existence throws our understanding of natural formations into chaos. Hexagons aren't unheard of in nature, think of honeycombs or Saturn's North Pole vortex, but those occur on planetary scales shaped by simple physics. This is different. The glowing hexagon emits energy signatures unlike anything else in the galaxy. Bursts of gamma radiation timed with eerie precision, as if synchronized by some unseen clock. Its surface isn't solid, it's a mesh of intersecting plasma filaments, each strand vibrating at frequencies that make no sense under known astrophysical models. Theories about its origins range from the plausible to the extraordinary. Could it be the aftermath of a hyper-advanced alien megastructure, a beacon, or even a failed experiment? The idea isn't as far-fetched as it sounds. In the 1960s, physicist Freeman Dyson proposed that advanced civilizations might build massive energy-harvesting structures in space. While most scientists dismiss this as speculative, the hexagon's unnatural symmetry keeps the debate alive. but let's assume it's natural for a moment. Some researchers argue it could be a rare type of plasma crystal, forged in the aftermath of a supernova where shock waves collided at just the right angles. Others suggest it's a cosmic whirlpool, a knot in space-time where magnetic fields have twisted into this bizarre shape. There's even a fringe hypothesis that it's a universe scar, a remnant from when our universe collided with another during the Big Bang, leaving behind a geometric wound in reality itself. What's undeniable is its effect on its surroundings. Stars near the hexagon show abnormal spectral lines, their light polarized in concentric rings. Dust clouds curve around it in perfect hexagonal spirals, as if space itself is bending to its will. And then there's the sound. Yes, sound. Converted into audio frequencies, its radiation pulses produce a haunting harmonic hum, a single sustained note that resonates across light years. Ongoing studies are focused on two burning questions. How does it maintain its shape against the chaos of interstellar space? And why hasn't entropy, the universe's relentless push toward disorder, eroded it into randomness? Every answer leads to 10 new questions, and that's what makes this object so thrilling. Whether it's a natural marvel or something far stranger, the glowing hexagon forces us to confront how little we truly understand about the architecture of the cosmos. One thing's certain, if we ever crack its secrets, the implications will ripple through every field of science. It could redefine how we think about energy, matter, and even the possibility of life beyond Earth. Until then, it remains one of NGC 262's most tantalizing puzzles, a geometric scream in the dark, demanding to be decoded. Amidst the cosmic wonders of NGC 262, few objects defy expectations as boldly as the Silent Pulsar. Picture the universe's typical pulsars spinning neutron stars that blast beams of radio waves across space like cosmic lighthouses. Their rhythmic pulses so predictable we use them as celestial clocks. Now imagine one that breaks all the rules, a pulsar that spins just as fast, just as powerfully, but broadcasts nothing. No radio whispers, no telltale beeps, just silence. That's exactly what astronomers found here, and its discovery flipped decades of pulsar science on its head. This enigma wasn't found the usual way. Most pulsars reveal themselves through their radio signatures, but the Silent Pulsar left astronomers empty-handed until gamma-ray telescopes caught its glow. Unlike its chatty cousins, this object floods space with high-energy gamma radiation while remaining eerily mute in every other wavelength. It's like finding a roaring bonfire that casts no shadow, a contradiction that challenges everything we thought we knew about how neutron stars behave. So what's behind this radio silence? One leading theory suggests its magnetic field is aligned in a way that funnels all its energy into gamma rays, leaving no leftovers for radio emissions. Imagine a garden hose with the nozzle twisted just so instead of spraying in all directions, the water jets out in a single, concentrated stream. If the Silent Pulsar's magnetic field is similarly focused, it could explain why we only see its gamma-ray scream while the radio waves vanish into the void. But there's a twist. Some researchers argue this might not be a pulsar at all, but something far stranger, a magnetar in disguise. Magnetars are neutron stars with unimaginably strong magnetic fields, capable of wrenching spacetime itself. Normally, they're notorious for violent X-ray outbursts, not steady gamma-ray hums. Yet if the Silent Pulsar is a magnetar operating in a never-before-seen mode, it could rewrite the textbook on how these extreme objects evolve. Then there's the possibility we're witnessing a cosmic phase transition, a pulsar mid-metamorphosis. Neutron stars aren't static. Over millennia, their magnetic fields decay, their spins slow, and their emissions shift. Could this be a snapshot of a pulsar shedding its radio voice as it ages into a new, quieter state? If so, catching it in this act is like stumbling upon a butterfly halfway through its emergence from a chrysalis, a rare glimpse into a process we've only theorized. The implications ripple far beyond NGC 262. If such silent pulsars are common, we've been missing a hidden population of neutron stars all along, their gamma-ray whispers drowned out by the radio chatter of their louder siblings. It forces us to ask how many more are out there, invisible to our traditional searches. Every new scan of the sky could reveal more of these quiet rebels, each one a reminder that the universe always has another card up its sleeve. For now, the silent pulsar remains a cosmic paradox, a beacon that refuses to signal, a spinner that hides its rhythm. It's a testament to how much we still have to learn about the life cycles of stars, the extremes of physics, and the secrets tucked away in the quiet corners of galaxies. And as long as it keeps spinning in silence, it will keep drawing astronomers back, daring them to listen more closely to what the cosmos isn't saying. The stars of NGC 262 hold countless mysteries, but few are as visually hypnotic as the Mirror Cluster, a group of 7 stars that shouldn't reflect light, yet do so with impossible precision. Imagine standing between 2 mirrors, watching your reflection bounce back and forth into infinity. Now picture that same effect unfolding across light years, with stars acting as both light source and mirror, their glow echoing between them in perfect synchronicity. That's the enigma astronomers face here, a celestial hall of mirrors where starlight doesn't just travel, it multiplies. Normally, stars emit light outward, their photons streaming into the void. But in this cluster, observations show something bizarre. When one star brightens, its neighbors brighten moments later, not from internal changes, but as if they're catching and reflecting that light, despite being too far apart for conventional reflection to occur. The timing is too exact, the intensity too matched. It's like watching a cosmic game of catch where the ball moves faster than physics allows. So what's really going on? The leading theory points to gravitational lensing, the phenomenon where massive objects warp spacetime to bend light around them. But this isn't ordinary lensing. Instead of magnifying distant objects or creating Einstein rings, the cluster's gravitational field seems to be folding light back onto itself, trapping photons in a loop between stars. Some researchers compare it to a quantum entanglement effect, but on a stellar scale, as if the stars share an invisible tunnel through which light teleports. Then there's the material angle. Spectrographs reveal traces of an unknown compound in the interstellar medium here, something that absorbs specific wavelengths before re-emitting them seconds later. Could this be a naturally occurring mirror material, a substance that bounces light with near-perfect efficiency? On Earth, we engineer metamaterials for cloaking devices, but nature has never shown us anything like this. If such a material exists naturally, it could revolutionize optics, energy harvesting, even our understanding of cosmic dust. But the most unsettling detail: the reflections aren't static. Over months of observation, the lag time between stellar pulses has shortened, as if the cluster is learning to reflect light more efficiently. It's an absurd notion. Stars don't adapt, yet the data refuses to cooperate with simpler explanations. Could dynamic dark matter be at play, its invisible particles rearranging to tweak the cluster's optical properties? Or are we seeing the fingerprints of a higher dimensional structure where light takes shortcuts through folded space? The mirror cluster doesn't just defy expectations, it holds up a mirror to the gaps in our knowledge. Every conventional model fails to fully explain its behavior, leaving scientists oscillating between awe and frustration. What's clear is this: if we can unravel how these stars communicate their light, it could redefine our grasp of gravity, quantum physics, and the very nature of cosmic connectivity. For now, it remains one of NGC 262's most dazzling puzzles, a place where the universe seems to be showing off, proving once again that the rules we know might just be the tip of the cosmic iceberg. Among the swirling chaos of NGC 262, where stars are born and die in violent brilliance, there lies a cosmic contradiction: the frozen supernova. This remnant doesn't behave like any other stellar explosion we've witnessed. Instead of expanding outward in a fiery shockwave, it hangs suspended as if time itself has stopped. Normally, supernova remnants spread for centuries, their debris stretching light years into space. But this one, it's locked in place, a ghostly snapshot of destruction preserved in the void. At first glance, it looks like a celestial still life, a delicate lacework of gas and dust glowing in hues of sapphire and emerald. But peer closer, and the anomaly becomes undeniable. Measurements taken over decades show no discernible movement. The outermost filaments, which should be racing outward at thousands of kilometers per second, are frozen mid-flight. It's as if someone hit pause on the universe, leaving this explosion trapped between moments. So what could possibly halt a supernova in its tracks? One leading theory points to magnetism on an unimaginable scale. Neutron stars, the dense cores left behind by supernova, can generate magnetic fields trillions of times stronger than Earth's. If this star's core collapsed into a magnetar, a neutron star with even more extreme magnetism, its field might be acting like an invisible cage, gripping the expanding debris and holding it in place. Picture a tornado frozen solid, its fury contained by some unseen force. That's the level of control we're talking about here, but magnetism alone might not explain everything. Another possibility involves dark matter, the invisible glue that holds galaxies together. If this supernova detonated within an unusually dense knot of dark matter, the gravitational tug from those unseen particles could be counteracting the explosion's outward push. It'd be like trying to run through waist-deep water. The energy's there, but something invisible is slowing it down. Simulations suggest dark matter halos could distort spacetime enough to trap a supernova's remnants, but we've never seen proof until now. Then there's the wild card, quantum locking. In labs on Earth, scientists can levitate superconductors over magnets using quantum effects that freeze them in place. Could some version of this be playing out on a cosmic scale? If conditions inside the remnant are just right, if temperatures and magnetic fields align in a freakish perfect storm, quantum mechanics might be overriding classical physics, locking the debris in an unchanging state. The implications are staggering. If we can decode how this supernova defies the laws of motion, it could reshape our understanding of stellar deaths, dark matter interactions, even the limits of quantum physics. And the discoveries might not stop there. Frozen supernova could be cosmic signposts, marking regions where dark matter clumps or spacetime behave strangely. They might even serve as natural laboratories, letting us study processes we could never recreate on Earth. For now, the frozen supernova remains a riddle wrapped in an enigma, suspended not just in space, but between what we know and what we've yet to imagine. Every observation peels back another layer, revealing just how much we still have to learn about the forces that shape the universe. And as long as it lingers there, unchanging, it will keep challenging us to rethink the rules, one frozen moment at a time. There's a rule in astronomy: quasars don't just vanish. These blazing beacons, powered by supermassive black holes feasting on gas and dust, are some of the most stable light sources in the universe, often shining for millions of years without flickering. But in NGC 262, astronomers watched in disbelief as a quasar that had burned bright for decades suddenly winked out of existence, like a candle snuffed by an unseen hand. One moment it was there, pumping out enough energy to outshine entire galaxies. The next, darkness, no fade, no warning, just silence. This wasn't just unusual, it was supposed to be impossible. The first clue to this cosmic disappearing act came when telescopes scanning the galaxy noticed a gap in the quasar's otherwise steady light curve. Follow-up observations revealed something even stranger: the accretion disk. The swirling ring of superheated material that feeds the black hole and generates the quasar's brilliance had vanished too. It wasn't dimmed or obscured, it was gone, as if someone had pulled the plug on the universe's most powerful engine. So what could annihilate a quasar so completely? One leading explanation involves a catastrophic collapse of the disk itself. Imagine a black hole's gravity finally overcoming the outward push of orbiting gas, causing the entire disk to spiral inward in one sudden catastrophic plunge. It'd be like watching a whirlpool drain in an instant, swallowing every drop of water at once. If this happened, the black hole would briefly flare with unimaginable brightness as it devoured its meal, then go dark, its fuel exhausted. But here's the catch. Simulations suggest such an event would take centuries, not the mere weeks astronomers observed. Another theory points to a cosmic sleight of hand, a rogue star or gas cloud passing directly between us and the quasar, acting like a celestial curtain. But for something to block all wavelengths of light so completely, it'd need to be unimaginably dense, a structure with no known natural counterpart. Some have even speculated about engineered megastructures, though most scientists favor less exotic explanations. Then there's the space-time twist. Could the quasar's light have been diverted by an intervening black hole's gravitational lens, bending its rays away from Earth like a cosmic prism? It's plausible, but lensing usually distorts light, doesn't erase it entirely. Unless, and this is where it gets wild, the alignment was so precise that the lensing effect created a perfect shadow, redirecting every photon away from our line of sight. The most unsettling possibility: we're witnessing the birth of a new type of astrophysical phenomenon, one where black holes can switch their quasars off like a lamp. If that's true, it suggests entire galaxies might flicker in and out of visibility across the cosmos, playing hide and seek on scales we've never imagined. Surveys are now scouring old data for other vanished quasars, searching for patterns that might unlock this mystery. For now, the vanishing quasar stands as a humbling reminder. Even the most constant giants of the universe can defy expectation. Whether it's a freak accident or a sign of deeper physics at work, its disappearance challenges us to rethink how black holes feed, how light travels, and what secrets might still lurk in the shadows between the stars. And somewhere out there, in the depths of NGC 262, a darkness lingers, waiting perhaps to ignite anew. In the quiet expanse of NGC 262, two galaxies perform a dance unlike any other. A chaotic, almost rebellious waltz that defies the orderly orbits we expect from celestial neighbors. Meet the dancing galaxies, a pair locked not in the graceful spirals of typical galactic interaction, but in a frenetic, unpredictable tango. Each seems to leap away from the other, only to be yanked back by unseen strings, their movements erratic, their paths scribbling jagged lines across the cosmos rather than smooth curves. At first glance, their motion appears impossible. Galaxies bound by gravity should follow predictable trajectories like planets around a star, but these two, they zig when they should zag, accelerate when they should slow, as if the laws of physics are being rewritten in real time. Some frames show them hurtling toward each other at breakneck speeds, only to veer apart moments later, their arms twisting into distorted shapes from the gravitational strain. It's the kind of chaos that keeps astronomers up at night, scrambling for explanations. The leading theory involves dark matter, the invisible scaffold of the universe. Most galaxies are embedded in vast halos of this mysterious substance, which guides their motions like an unseen hand. But here, the dark matter distribution might be warped, clumped in uneven pockets that tug the galaxies in conflicting directions. Imagine two ice skaters holding hands, each suddenly yanked by separate ropes. Their dance would become a struggle. That's what could be happening on a galactic scale, with dark matter's uneven grip turning a stately orbit into a cosmic wrestling match. Then there's the timing. Normally, galactic dances play out over billions of years, but these two seem to be moving in fast forward. Some researchers suggest they might be caught in a slingshot effect, where a third, unseen galaxy, or even a runaway black hole flung them into this frenzy. Others wonder if we're witnessing the aftermath of a near collision so violent it left their gravitational fields permanently tangled, like threads knotted beyond repair. The implications ripple far beyond NGC 262. If dark matter can warp galactic motion this dramatically, our models of how galaxies form and evolve might need revisiting. Could entire clusters be dancing like this, hidden in plain sight? And what does it mean for the fate of these two galaxies? Normally, such close encounters end in mergers, but their chaotic paths suggest they might never settle, or doomed to this endless, erratic ballet. Every observation peels back another layer of mystery. The dancing galaxies don't just challenge our understanding of gravity, they whisper that the universe's choreography is far more complex than we ever imagined. And as long as they keep spinning in defiance of the rules, they'll remain one of NGC 262's most mesmerizing enigmas, a reminder that even the cosmos loves to break into unexpected moves. Drifting alone through the interstellar void of NGC 262, an orphaned world defies every expectation of what a planet should be, the hollow planet. At first glance, it appears unremarkable, a dark, rocky sphere about the size of Neptune tumbling silently through space. But when astronomers measured its density, the numbers didn't just raise eyebrows, they shattered assumptions. This planet weighs less than a tenth of what it should, as if someone scooped out its insides and left behind a cosmic eggshell. The mystery deepens when you consider how such a structure could exist naturally. Planets form from swirling disks of gas and dust, their materials compressing under gravity into dense, layered spheres. Yet this one behaves like a celestial Russian nesting doll, its outer crust rigid, its interior suspiciously light. Seismic simulations suggest it might be riddled with caverns so vast they occupy 90% of its volume. Some passages could stretch for thousands of kilometers, twisting into labyrinthine tunnels where sound would echo for hours. But how does a planet become hollow? One theory points to an ancient cataclysm. Imagine a young gas giant bombarded by asteroids, its volatile gases stripped away until only a brittle skeleton remained. Alternatively, tidal forces from a long-vanished star might have stretched and fractured its core, leaving behind a porous husk. There's even a wilder possibility, the remnants of a protoplanetary collision, where two worlds smashed together but failed to fully merge, creating a fractured, empty shell. Then there's the elephant in the room. Could this be artificial? The idea isn't as far-fetched as it sounds. In the 1960s, physicist Freeman Dyson speculated about civilizations building megastructures around stars to harness energy. Could an advanced society have hollowed out a planet, turning it into a vast habitat or storage vault? The planet's surface shows strange geometric scarring, not unlike the markings left by mining operations, but on a scale that dwarfs human engineering. If natural processes can't explain these features, we're left with a chilling question: who or what might have carved this world from the inside out? What's undeniable is the hollow planet's effect on its environment. Its weak gravity bends passing starlight in odd ways, creating lensing artifacts that flicker like cosmic Morse code. Dust clouds spiral around it in unnatural patterns, as if caught in an invisible web. And then there are the radio whispers, faint, rhythmic pulses detected by deep space antennas, their origins untraceable but their timing too precise to dismiss as static. Some researchers argue this could be a natural radio pulsar buried in the planet's crust, its signals distorted by the hollow interior. Others wonder if we're picking up echoes of something far older, a beacon perhaps, or a warning. Until we send a probe through those cavernous depths, the hollow planet will keep its secrets locked away, a silent enigma drifting through the dark. Whether sculpted by violence, time, or something beyond our understanding, this world challenges our definitions of what's possible. It's a reminder that the universe doesn't just create planets, it engineers paradoxes. And as long as this hollow giant wanders NGC 262, it will beckon us to question not just how planets form, but why some break the mold entirely. In the heart of NGC 262, a star defies the relentless march of cosmic time. Meet the time-dilated star, a celestial anomaly aging at a fraction of the speed of its stellar neighbors. While most stars live and die by the steady tick of universal clocks, this one exists in slow motion, as if swimming through an ocean of treacle while the galaxy rushes past. Observations reveal its nuclear reactions lagging behind, its light stretched into deeper reds, and its life cycle extended far beyond what physics should allow. It's not just a star, it's a time capsule preserving a moment the universe has long since left behind. The culprit behind this temporal trickery, Einstein's theory of relativity. When an object moves near light speed or lingers in an intense gravitational field, time for it slows relative to the outside world. Near a black hole, for example, minutes could stretch into years elsewhere. But the time-dilated star presents a puzzle. It isn't orbiting a black hole, and its velocity, while fast, doesn't approach relativistic speeds. So why does it behave as if trapped in a gravitational funhouse? One explanation points to a hidden dance partner, a neutron star or quark star lurking unseen, its gravity warping spacetime enough to twist time without the visible cues of a black hole. Alternatively, the star might be tumbling through a region of spacetime still recoiling from an ancient collision between cosmic strings, hypothetical scars from the Big Bang that could stretch and compress time like taffy. The star's light tells an even stranger story. Spectral lines shifted far beyond what Doppler effects alone can explain suggest its very atoms are vibrating in slow motion. If you could stand on its surface ignoring the crushing heat and gravity, clocks would tick glacially and nuclear fusion in its core would unfold like a film played at half speed. For every century that passes in the galaxy, mere decades might elapse here, a discrepancy that challenges our models of stellar evolution. What fascinates scientists most isn't just the star's defiance of time, but what it implies about the galaxy's history. If time dilation can occur under conditions we've yet to map, entire populations of stars might be hiding in plain sight, their true ages masked by the warp and weft of spacetime. The time-dilated star could be the first clue in a much larger mystery, one that forces us to ask, how many other cosmic clocks are ticking out of sync, and what secrets might they hold about the universe's most extreme environments? For now, this star remains a temporal rebel, a flickering enigma reminding us that time, like space, is far more malleable than we once believed, and as long as it burns slow and steady against the galactic current, it will keep challenging us to rethink not just how stars age, but how the fabric of reality itself is woven. Stretching across the void of NGC 262 like a living curtain of light, the cosmic jellyfish is a nebula that refuses to behave like the cold, static clouds we're used to. Its tendrils, some stretching over 3 light-years long, throb with rhythmic pulses, expanding and contracting as if breathing. Most nebulae glow steadily, illuminated by nearby stars or fading supernova remnants. But this one dances, its filaments twisting in synchronized waves that ripple outward every 72 hours like clockwork, as if controlled by some unseen cosmic metronome. The first mystery lies in what's powering this eerie pulse. Normal stellar winds, the streams of charged particles blowing off stars, create chaotic, asymmetrical shapes in nebulae. Yet the jellyfish's movements are too orderly, too precise. Some researchers suspect an ultra-dense neutron star might be lurking at its core, spinning rapidly and firing jets of particles that whip the surrounding gas into this synchronized motion. Picture a submersible stirring the ocean depths, creating spirals in its wake, except here, the ocean is interstellar plasma, and the submersible is a stellar corpse with a magnetic field strong enough to shred atoms. But magnetism alone might not explain the timing. The 72-hour cycle matches no known pulsar rotation or binary star orbit in the region. That's led others to propose something far stranger: resonant harmonics. Just as plucking a guitar string creates standing waves, the nebula's structure might be vibrating at its natural frequency, amplified by some external force. If true, the entire nebula could be acting like a colossal musical instrument, its tendrils humming in tune with the galaxy's hidden vibrations. Then there's the color. Most emission nebulae glow red from hydrogen alpha light, but the jellyfish flickers between ultraviolet and deep indigo, suggesting the presence of elements we rarely see in such concentrations: ionized oxygen, doubly charged neon, even traces of an unidentified spectral line nicknamed jellyfish blue. Some speculate these elements hint at a recent exotic supernova, one that fused matter in ways we've never observed. Others wonder if the nebula is filtering light through an undetected quantum phenomenon, bending photons into these unusual hues. Perhaps the most unsettling detail is the tendrils' movement. They don't just pulse, they recoil. High-resolution time-lapses show the outermost filaments snapping back after each expansion, as if encountering resistance. Could they be colliding with an invisible medium dark matter, perhaps? Or is space-time itself slightly stiffer here, creating a subtle drag? The answer might rewrite how we think about the interstellar medium's texture. For now, the cosmic jellyfish remains one of NGC 262's most mesmerizing spectacles, a reminder that even the quietest corners of space can harbor motion, rhythm, and secrets we've yet to decode. Whether it's a magnetic marionette, a resonant echo, or something beyond our current physics, each pulse is a clue, and with every throb, it invites us to listen more closely to the music of the cosmos. In the vast expanse of NGC 262, where cosmic oddities seem to multiply by the day, nothing quite prepares you for the sheer absurdity of the gravity well anomaly. This isn't just a region where gravity weakens, it's a place where the fundamental force flips its script entirely. Picture tossing a rock into a pond, only to watch it fly upward instead of sinking. That's the kind of defiance at play here, a zone where matter isn't pulled inward but violently repelled, as if space itself has developed an allergy to mass. At the Anomalies' heart lies a void roughly the size of our solar system, a place where stars don't just drift, they recoil. Telescopes have captured rogue planets and even small neutron stars skirting its edges, only to be flung away at speeds that defy orbital mechanics. Gas clouds approach, stretch into bizarre, elongated shapes, then scatter like frightened birds. It's as if some unseen hand has rewritten Newton's laws in real time, leaving physicists to wonder whether they've stumbled upon a glitch in the universe's code. So what could possibly invert gravity's grip? The leading explanation points to quantum vacuum fluctuations, a sea of fleeting particles and antiparticles that constantly pop in and out of existence. Normally, these cancel each other out, but theoretical models suggest that under extreme conditions, they might generate negative energy densities, effectively creating repulsive gravity. It's like trying to stand on a trampoline while someone beneath you pushes up with equal force. The surface beneath your feet would no longer obey the usual rules. Then there's the space-time warp theory. Einstein showed us that mass bends the fabric of the cosmos, but what if that fabric could crease in on itself, forming a kind of cosmic hill instead of a valley? In such a region, objects wouldn't roll downward, they'd roll away. Some mathematicians argue that exotic matter, a hypothetical substance with negative mass, could twist space-time into this unnatural shape, though no one's ever observed such matter outside of equations. But the real enigma lies in the anomaly's stability. Most cosmic oddities are fleeting: supernova fade, quasars dim, yet this gravitational rebellion has persisted for centuries. That's led to wilder speculation. Could this be the work of a primordial black hole, one so ancient it's begun to unravel the very fabric of space-time around it? Or even a relic from a previous universe, a knot of physics so alien it operates by different rules entirely. The implications are as vast as they are unsettling. If repulsive gravity can exist naturally, it challenges everything from our models of star formation to the fate of the universe itself. Dark energy, the mysterious force accelerating cosmic expansion, might share a kinship with this anomaly, hinting that we're witnessing a microscopic version of whatever's tearing the cosmos apart on the grandest scales. For now, the gravity well anomaly remains a cosmic paradox, a place where the universe shrugs off its own rulebook. Whether it's a quantum quirk, a space-time scar, or something beyond our current theories, one thing's certain: it's a reminder that even gravity, the force we thought we understood, still has secrets to spill. And until we crack its code, this defiant patch of NGC 262 will keep pushing the boundaries of what we call possible. Drifting silently through the outer reaches of NGC 262, the crystal asteroid is a cosmic jewel unlike anything else in the galaxy. Most asteroids are rough, pockmarked chunks of rock and metal, but this one gleams with geometric perfection, its surface a mosaic of interlocking crystalline facets that catch the light like a prism. Scans reveal it's composed entirely of mineral structures so pure they'd put Earth's finest diamonds to shame. Some sections form perfect hexagons, others spiral into fractal patterns, as if the asteroid were sculpted by an artist with an obsession for symmetry. The first mystery is how such an object could exist. Crystals this large and flawless typically form under intense, sustained pressure conditions found deep within planets, not floating adrift in space. One theory suggests this asteroid is all that remains of a shattered exotic planet, one whose mantle was rich in rare minerals like beryllium oxide or even theorized hypercrystals with lattice structures unknown on Earth. A cataclysmic collision could have blown the planet apart, launching this fragment into the void where it now drifts, a lone survivor of a lost world. But there's a hitch: the asteroid's composition doesn't match any known planetary crust or mantle. Spectrographic analysis detects traces of elements arranged in ways that defy natural crystallography, with atomic bonds aligning at angles that shouldn't be stable. Some researchers speculate it might be a chunk of a white dwarf's crust, the ultra-dense remnants of a dead star's outer layers, forged in temperatures and pressures so extreme they birthed crystals unlike anything in our solar system. Then there's the light. When nearby stars illuminate the asteroid, it doesn't just reflect their glow. It amplifies it, focusing light into concentrated beams that flicker like cosmic lighthouses. This isn't just a trick of its polished surface. The crystal lattice itself seems to act as a natural laser cavity, a phenomenon only possible if its internal structure is flawlessly aligned on a molecular level. Could this be a fragment of some ancient megastructure, a piece of alien technology lost to time? The asteroid's uncanny regularity fuels speculation, but the truth might be even stranger. Some models suggest it could be a seed crystal from the early universe, a primordial relic that grew in the chaos of the Big Bang when the laws of physics themselves were still settling into place. For now, the crystal asteroid remains a glittering enigma, a fragment of cosmic artistry that challenges our understanding of how matter organizes itself. Whether it's a piece of a shattered world, a stellar relic, or something beyond our current science, one thing's certain: it's proof that the universe has a flair for the extraordinary and a habit of hiding its most breathtaking creations in plain sight. Amidst the cosmic symphony of NGC 262, one icy wanderer refuses to travel in silence: the singing comet. Unlike the muted, drifting snowballs we're accustomed to, this celestial nomad broadcasts a haunting melody, its radio emissions harmonizing into precise, almost musical frequencies. Picture the deep hum of a cello string vibrating through the void, its notes shifting as the comet pirouettes around stars. At first, astronomers assumed their instruments had malfunctioned until the pattern repeated, note for note, across multiple observatories. This wasn't static, it was a song. The comet's voice originates from its nucleus, where solar wind particles slam into its frozen surface, ionizing molecules and creating a shimmering plasma envelope. Normally, this process generates chaotic radio noise, but here, something transforms that chaos into order. The key lies in the comet's unusual composition. Layers of ice and dust arranged in precise, crystalline lattices that vibrate like tuning forks when energized. As solar wind rushes through fractures in the nucleus, it excites these structures, causing them to resonate at specific frequencies like wind whistling through a canyon, but on a subatomic scale. But there's a twist. The harmonies aren't random. They follow mathematical ratios found in musical scales, with intervals matching the golden ratio, a proportion often tied to aesthetic beauty in nature. Some sections of the comet emit bass tones, while others produce overtones, creating an eerie chorus that shifts as the nucleus rotates. It's as if the universe composed a lullaby using ice and starlight as its instruments. Theories about this phenomenon range from the mundane to the extraordinary. One camp argues it's a fluke of geometry, a perfect storm of ice density and solar wind pressure that won't last. Others propose the comet's structure was sculpted by gravitational tides during a close encounter with a neutron star, aligning its layers into a natural soundboard. Then there's the fringe idea: could these vibrations be intentional? On Earth, we use resonant frequencies to transmit information. Could the comet be an icy antenna relaying signals we're only beginning to decode? What's undeniable is the comet's effect on its surroundings. Passing dust clouds ripple in synchronous waves, as if swaying to its rhythm. Nearby asteroids with similar compositions have been found emitting faint, matching harmonies, suggesting this might be a previously overlooked cosmic phenomenon. If so, the singing comet isn't just a curiosity, it's a Rosetta Stone for understanding how celestial bodies communicate through vibrations we've only just learned to hear. As it journeys deeper into the galaxy, its song evolves, offering new verses with each stellar pass. Whether it's a quirk of physics or a message in a bottle from the cosmos, one thing's certain: the universe has a soundtrack, and this icy minstrel is its most enigmatic performer. Somewhere in the depths of NGC 262, an unseen leviathan prowls the invisible giant. This cosmic phantom weighs as much as a dozen suns, bending starlight with its gravity, yet it emits no light, no heat, no radio whispers. Telescopes stare straight through it as if it weren't there at all. The only evidence of its existence, the way nearby stars jerk abruptly in their orbits, their paths kinked by something massive lurking in the dark. What makes this object so unnerving is how thoroughly it defies detection. Black holes typically betray themselves with X-ray screams from their accretion disks, and dark matter halos are inferred from subtle galactic rotations. But it's a gravitational ghost, all mass, no footprint. Even the most sensitive neutrino detectors come up empty. It's as if the universe forgot to give this thing a shadow. One compelling theory points to a primordial black hole, a relic from the universe's first moments. Unlike stellar black holes, born from collapsing stars, these ancient anomalies could have formed when the newborn cosmos was still a seething froth of energy. Denser patches might have collapsed directly into black holes, some as small as asteroids, others as massive as galaxies. If one of these time-worn titans survives here, it could explain the invisible giant's pure gravitational presence, a fossil from before light itself had fully escaped the Big Bang's afterglow. Then there's the dark matter angle. Most dark matter is thought to be a diffuse sea of invisible particles, but some models suggest it could clump into dense nuggets like cosmic icebergs drifting through space. If such a clump, what physicists call a dark matter mini-halo, lurks here, its gravity would warp its surroundings while remaining utterly transparent. The idea isn't as far-fetched as it sounds. Simulations show dark matter could theoretically condense under its own gravity, especially near galactic cores where densities run high. The real puzzle is why we haven't found more of these invisible giants. If they're common, their gravitational fingerprints should be scattered across every galaxy. Yet NGC 262's Phantom stands nearly alone, a cosmic oddity that forces us to ask, are we missing an entire population of hidden monsters, or is this one a rare fluke, a cosmic misfit that stumbled into existence against all odds? Whatever the answer, the invisible giant taunts us with a fundamental truth. The universe hides its most massive secrets in plain sight. It's a reminder that for all our telescopes and detectors, some corners of reality remain stubbornly, magnificently dark. And until we learn to see the unseen, mysteries like this will keep pulling at the edges of our understanding, silent and relentless as gravity itself. The skies of NGC 262 hold a spectacle that would make even Zeus pause: the lightning storm nebula, a celestial tempest where bolts of plasma crackle non-stop across light years of space. Unlike the gentle glows of typical nebulae, this one crackles with raw energy, its filaments alive with electrical discharges powerful enough to vaporize planets. Imagine standing on a world beneath these skies instead of a starry night. You'd witness an endless fireworks display with arcs of blue-white lightning stretching far beyond the horizon. What fuels this cosmic storm? The answer lies in the nebula's chaotic heart, where two forces collide: extreme magnetism and runaway ionization. At its core, a cluster of young, hyperactive stars bombards the surrounding gas with ultraviolet radiation, stripping electrons from atoms and creating a seething plasma soup. But the real magic happens when this plasma encounters twisted magnetic fields. Think of them as cosmic power lines left behind by ancient supernovae. These fields channel the charged particles into focused paths, forcing them to slam together at nearly light speed. The result: continuous, cascading discharges that make earthly lightning look like static sparks. The sheer scale of these bolts defies belief. Some stretch over 8 light-years from end to end, carrying currents so strong they dwarf every power grid on Earth combined. Spectrographs reveal they're not just hotter than the Sun's surface, they're laced with exotic elements like ionized iridium and magnetically confined antimatter, substances rarely seen outside particle accelerators. This suggests the nebula might be a natural collider, a place where matter gets shredded and reforged under conditions we can't replicate in labs. But the most baffling part: the lightning follows patterns. High-speed observations show the discharges pulsing in fractal sequences, with smaller forks mirroring larger ones in perfect symmetry. Some researchers compare it to a self-organizing circuit, where plasma remembers previous pathways and reinforces them. Others speculate the entire nebula functions like a cosmic brain, with the lightning acting as synaptic flashes across a galactic-scale neural network. Whether it's a natural particle accelerator or something even stranger, the Lightning Storm Nebula forces us to rethink how energy behaves in the universe's most extreme environments. And as long as those electric tendrils keep flashing through the dark, they'll remind us that the cosmos isn't just vast, it's alive with currents we're only beginning to measure. 12,000 light-years apart, two stars in NGC 262 pulse in perfect unison, not just by chance, but as if sharing a single heartbeat. This is the quantum star and its invisible twin, locked in a dance so precise it defies the cosmic speed limit. Every flare, every dimming, every flicker occurs simultaneously across the void, with no delay for light to travel between them. It's as if they're not separate objects at all, but two parts of a single system connected by something deeper than gravity, faster than light. What we're witnessing mirrors a phenomenon once confined to quantum labs: entanglement. On Earth, scientists entangle particles so that altering one instantly affects its partner, regardless of distance. But that's with electrons or photons in controlled experiments. For entire stars, each a churning cauldron of plasma and magnetic fields to exhibit this behavior. That shouldn't be possible. The energy scales alone would tear any quantum link apart, yet here they are, whispering secrets across the galaxy as if space means nothing. The implications stagger physicists. If entanglement can scale up to stellar proportions, it challenges our bedrock assumption that quantum weirdness fades in larger systems. Some theorists argue these stars might be threaded by cosmic strings, hypothetical spacetime defects left from the Big Bang, acting as quantum tunnels that bypass conventional distance. Others propose they're remnants of a binary star torn apart by a black hole, its halves still tethered by microscopic wormholes. Then there's the radical idea that space itself has a hidden quantum layer, and these stars are accidental antennas resonating with it. But the real shocker, this isn't just about stars. If quantum links can persist on such monstrous scales, entire galaxies might be subtly synchronized in ways we've never detected. Supernova could trigger distant explosions, black holes might share information. The universe, instead of a collection of isolated objects, could be a vast, interwoven network where everything is, in some faint, fundamental way, touching everything else. For now, the quantum star remains a cosmic koan, a riddle written in starlight. Whether it's a fluke or the first thread of a larger tapestry, one thing's clear: the universe just handed us a new rulebook. And somewhere in those synchronized pulses lies a truth that could unravel or rewrite our understanding of reality itself. Nestled within NGC 262 lies a cosmic kaleidoscope, the fractal galaxy, where spiral arms don't just curve gracefully but branch into infinitely repeating patterns, like a celestial snowflake magnified across light years. Zoom in on any segment of its structure, and you'll find the same intricate motifs recurring at smaller scales. Walls within walls, arcs within arcs, a universe of detail echoing itself endlessly. This isn't just aesthetics, it's a mathematical marvel, a place where nature seems to have scribbled its blueprints in the language of fractals. How does such precision emerge in the chaos of space? Natural processes offer some clues. Normally, galactic arms form through density waves, ripples in the disk that compress gas and trigger star formation. But here, astronomers suspect a rare feedback loop. Stellar winds and supernova shockwaves might be carving the galaxy's gas into finer and finer subdivisions, like a sculptor refining clay with each pass. Picture a pebble dropped in a pond, its ripples intersecting with new pebbles dropped at just the right intervals, creating overlapping patterns that amplify into fractal perfection. Then there's the gravitational puzzle. Hidden black holes or dark matter filaments could be acting like cosmic loom shuttles, weaving the galaxy's matter into these recursive shapes. Simulations show that if multiple smaller galaxies merged here long ago, their overlapping tidal forces might have stamped these patterns into the surviving structure, leaving behind a gravitational fingerprint that repeats like a hall of mirrors. But what if nature didn't act alone? The fractal galaxy's geometry is so unnervingly precise, it sparked speculation about intelligent design. Could an advanced civilization have harnessed nanotechnology, or something far beyond it, to rearrange matter at a galactic scale? Theorists point to hypothetical Dyson forests, where swarms of megastructures could manipulate star formation like pixels on a screen. Even if that's a stretch, the galaxy's patterns challenge us to ask, where's the line between natural order and something more? The most tantalizing detail lies in the galaxy's star clusters. Unlike the random scattering seen elsewhere, these groups align along the fractal branches like pearls on a string, their ages matching the pattern's layers. It's as if each generation of stars inherited its predecessor's blueprint, building the galaxy's complexity over eons. Whether sculpted by chaos, design, or some undiscovered physics, the fractal galaxy stands as a testament to the universe's capacity for artistry, and a reminder that even the grandest structures might follow rules we've yet to decode. Deep within NGC 262, there's a patch of emptiness that talks back the echoing void. This region of space, roughly the size of a solar system, doesn't just absorb signals like the cosmic silence we're used to. It throws them back, twisted and amplified, as if space itself has grown an echo chamber. Astronomers first stumbled onto this anomaly when a routine deep space probe fired a radar pulse into the void only to receive it back seconds later, warped beyond recognition. The pulse hadn't bounced off any detectable object. It had simply returned like a voice hurled into a canyon that shouldn't exist. What's weirder isn't just that signals echo, it's how they change. Some frequencies come back inverted, their waveforms flipped as if reflected by a cosmic mirror. Others return louder, carrying up to 5 times their original energy without any discernible power source. It's like shouting into a cave and hearing your whisper come back as a roar. The distortions aren't random either. Mathematical analysis reveals patterns, repetitions, delays, even harmonics that suggest something about this void is fundamentally reshaping the signals, not just relaying them. Theories about what's happening here range from the mind bending to the borderline supernatural. One camp argues this is a space-time loop, a region where gravity has warped the fabric of reality into a closed time-like curve, a literal knot in time. Signals entering might briefly travel backward before re-emerging, their journey through inverted time scrambling their structure. Others propose the void contains exotic matter with negative energy density, a substance that could reflect electromagnetic waves in ways normal matter can't. Imagine throwing a ball at a wall only to watch it rebound faster than you threw it. That's the kind of physics-defying behavior we're dealing with here. Then there's the holographic hypothesis. Some researchers suggest the void's boundaries might function like a cosmic recording surface, trapping information about any signal that enters and projecting a distorted copy back out. In this scenario, the void isn't empty at all, it's a densely encoded membrane, a sort of quantum etch-a-sketch that briefly holds onto whatever passes through it. If true, it could mean the universe has built-in mechanisms for storing and manipulating information we've only begun to glimpse, the most unsettling possibility. The echoes aren't just distortions, they're responses. A handful of scientists have noted that certain modulated signals, when sent into the void, return with what appear to be nested mathematical sequences, Fibonacci spirals, prime number arrangements, even approximations of fundamental constants. It's as if the void isn't just reflecting, it's computing, folding the signals through some hidden logic before spitting them back. Whether this is a quirk of physics or something more intentional remains an open question, one that keeps radio astronomers awake long into the night, tweaking their transmitters in hopes of catching the void's next whispered secret. For now, the echoing void stands as a cosmic conversation no one fully understands. Each returned signal is a cipher, a riddle wrapped in the universe's most enigmatic silence. And as long as it keeps talking back, we'll keep listening, because somewhere in those warped echoes might lie clues not just about this patch of space, but about the very nature of reality itself. Floating through the star-dappled reaches of NGC 262, the bioluminescent cloud pulses with an eerie, organic glow, a celestial spectre that seems more at home in Earth's midnight oceans than in the cold vacuum of space. Unlike the searing radiance of typical nebulae, this cloud shimmers with soft blues and greens, its light rippling in slow, undulating waves like the flicker of 1,000 fireflies. At times it brightens into sudden flares, then dims just as quickly as if breathing. The effect is so hauntingly lifelike, early observers dubbed it the Galaxies' ghost reef, a place where the cosmos itself appears to exhale light. What powers this otherworldly glow? The first clue lies in its spectrum. Most nebulae shine because their atoms are excited by ultraviolet light from nearby stars, emitting predictable wavelengths as they calm down. But the bioluminescent cloud's light signature is a mess of irregular spikes and troughs, with energy signatures that match no known atomic transitions. It's as if the cloud has its own internal chemistry, one that generates light through processes we've only seen in living organisms. Some researchers point to complex molecules like polycyclic aromatic hydrocarbons, carbon-rich compounds found in deep space dust, that might be resonating in unique ways. On Earth, similar compounds help produce the glow of bioluminescent plankton. Could this be a cosmic-scale version of that same phenomenon? Then there's the nuclear angle. Deep within the cloud, telescopes have detected trace amounts of radioactive isotopes like uranium and thorium, elements forged in supernova. When these decay, they release particles that can excite surrounding gas, creating a faint, persistent luminescence. But the math doesn't quite add up. The observed light is orders of magnitude brighter than these isotopes should produce, unless, of course, something is amplifying their effects. One controversial theory suggests the cloud might be threaded with microscopic neutron-rich filaments, relics from a nearby neutron star's explosion, acting like a natural nuclear reactor. Picture a nebula-sized Geiger counter, its entire structure crackling with silent, radioactive ticks. But the most tantalizing possibility is that we're seeing an entirely new form of light production. Some astrophysicists speculate the cloud could be a testing ground for exotic plasma physics, where magnetic fields twist and reconnect in ways that convert kinetic energy directly into light, bypassing traditional excitation pathways. It'd be akin to discovering a star that burns without fusion, a heresy against established science. Others whisper about quantum biofluorescence, where the cloud's molecules become entangled across vast distances, creating coordinated light bursts that mimic biological systems. The implications ripple far beyond NGC 262. If this glow stems from natural processes we've never catalogued, it could hint at hidden avenues for energy transfer in the universe, mechanisms that might explain everything from unexplained deep space flashes to the origins of life's own luminous chemistry. Or perhaps in its shimmering depths, the cloud is hiding something even more profound, a reminder that the line between cosmic and living phenomena might be thinner and stranger than we ever dared imagine. For now, the bioluminescent cloud keeps its secrets pulsing softly in the dark, a galactic enigma wrapped in living light. Whether it's a radioactive relic, a quantum fluke, or something beyond our current science, one thing's certain: it's teaching us that the universe's palette of light is far richer and more mysterious than we ever suspected. Among the countless moons orbiting gas giants in NGC 262, one stands out not for its size or color, but for its impossible composition, the metallic moon. This isn't just a rocky body with veins of ore. Its entire surface gleams like a polished anvil, reflecting starlight with a mirror's precision. Scans reveal a shell of nearly pure iron and nickel alloy, forged with a purity that defies natural processes. No volcanic flows or asteroid bombardments on record could produce such uniformity. It's as if someone took a celestial hammer to this world, beating it into a smooth, metallic husk. The first clue to this moon's origins lies in its scars. Unlike pockmarked moons elsewhere, its surface bears only shallow, elongated grooves, as if something skimmed its exterior like a stone across a pond. These marks align with trajectories of ancient asteroid swarms, suggesting the moon might have once had a rocky crust that was stripped away by relentless impacts over eons. But here's the catch: metal doesn't just accumulate like this. Normally, collisions would leave behind a mix of debris, not a seamless metallic veneer. Unless, of course, the impacts triggered something deeper. One theory points to a planetary-scale smelting event. Imagine a primordial moon rich in iron oxides, its core still molten. If a massive impactor struck at just the right angle, the shockwave could have sent seismic ripples through the mantle, forcing liquid metal upward in a global eruption. As this metallic tide met the vacuum of space, it might have cooled into the smooth shell we see today, a frozen splash of planetary innards. Supporting this, thermal scans detect residual heat patterns radiating in concentric rings like ripples from a pebble dropped in a forge. But there's a more unsettling possibility: refinement. On Earth, we extract metals from ore through industrial processes. Could this moon be evidence of something similar on a cosmic scale? Spectrographs show trace elements arranged in ratios found only in manufactured alloys, not natural deposits. Some researchers argue it's the remnant of a megastructure, perhaps a Dyson sphere component or a discarded, forged world from a long-vanished civilization. Others counter that natural ultra-high-pressure environments like those near a neutron star could have achieved similar results. The Moon's magnetic field adds another layer of intrigue. Most metal-rich bodies generate weak or chaotic magnetism, but this one pulses with a steady, planet-wide field, as if its entire shell were a unified conductor. That suggests its metal layer isn't just a coating, it's interconnected, possibly honeycombed with liquid channels or superconducting filaments. If true, the Moon might be less a dead world and more a dormant machine, its heart still flickering with forgotten energy. Whether sculpted by violence, time, or hands we can't yet imagine, the metallic Moon challenges our notions of how worlds form and what they might hide beneath their skins. Every reflection off its uncanny surface is a reminder the universe doesn't just create, sometimes it forges. Buried in the swirling arms of NGC 262 lies the aftermath of a cataclysm so violent it rewrote the rules of stellar destruction, the hypernova fossil. Unlike the symmetrical debris fields left by typical supernova, this remnant sprawls across space like a shattered stained glass window, its fragments glowing with energies that shouldn't exist. Gamma-ray telescopes first detected its pulse, a lingering scream of radiation with peaks and troughs that match no known stellar death throes. It's as if this explosion didn't just burn out, it malfunctioned, leaving behind a cosmic crime scene where the laws of physics seem broken. At the fossil's heart lies the real Enigma, a neutron star spinning slower than any on record, its surface crust cracked in fractal patterns that emit intermittent X-ray whispers. Normally hypernova, stellar explosions 100 times more powerful than supernova leave behind rapidly spinning pulsars or black holes. But this neutron star drifts lethargically, as if something drained its energy mid-collapse. The surrounding debris compounds the mystery, laced with rare isotopes like technetium and promethium, elements so unstable they vanish within millennia. Their presence suggests the hypernova's fury was laced with forces we've never observed, perhaps even tapping into exotic particle decays that shouldn't occur naturally. Then there's the radiation signature. Most hypernova flood space with a predictable mix of gamma rays and neutrinos, but this event left behind polarized gamma bursts, light waves oscillating in perfect unison, like soldiers marching in lockstep. Such coherence usually requires artificial amplification, like the lasers in Earth's laboratories, yet here it occurs naturally, stretching across light years. Some theorists argue the explosion might have been focused by an ultra-strong magnetic field, turning the entire event into a cosmic particle accelerator. Others speculate about quark nova, a hypothetical stellar death where neutrons dissolve into free quarks, releasing energies that dwarf conventional models. The most radical explanation: this wasn't just a star's death, it was a star's sabotage. Could a primordial black hole or dark matter asteroid have plunged into the star's core moments before collapse, injecting unstable energy that twisted the explosion from within? Ancient computer simulations hint that such collisions might trigger zombie hypernova, where the star briefly reignites after initial collapse, tearing itself apart in unpredictable ways. If true, the hypernova fossil isn't just a remnant, it's a celestial autopsy, revealing scars from a battle between matter and something far stranger. What's undeniable is the fossil's effect on its neighborhood. Nearby gas clouds shimmer with residual ionization, their molecules aligned in eerie, grid-like formations. Stars birthed from this material show abnormal metal ratios, their atmospheres seasoned by the hypernova's exotic fallout. It's as if the explosion didn't just end a star, it altered the chemistry of an entire galactic quadrant, leaving behind a fingerprint we're only beginning to decode. Whether it's a fluke of physics or a signpost to new stellar phenomena, the hypernova fossil forces us to confront an uncomfortable truth. The universe might harbor ways to destroy stars that we haven't even imagined. And as long as its fractured glow lingers in the dark, it will keep challenging us to rethink how stars live, die, and sometimes defy their own endings. In the heart of NGC 262, time itself seems to tick with mechanical perfection thanks to the clockwork pulsar, a celestial metronome whose pulses arrive so precisely they rival Earth's most advanced atomic clocks. While most pulsars spinning neutron stars that emit beams of radiation wobble ever so slightly in their rhythms, this one defies the chaos of space with intervals accurate to within a trillionth of a second over decades. It's as if the universe wound up a cosmic pocket watch and left it ticking in the void, each radio click marking seconds with unerring consistency. What sets this pulsar apart isn't just its precision, but the eerie purity of its signal. Typical pulsars exhibit glitches, sudden speed-ups or slowdowns caused by starquakes or magnetic shifts in their superfluid cores. The clockwork pulsar, however, shows no such irregularities. Its rotation remains flawlessly stable, as if its immense mass, greater than our Sun's, compressed into a sphere the size of a city, were balanced on frictionless bearings. Even more perplexing, its pulse profile, the shape of its energy bursts never distorts, implying an electromagnetic field of impossible symmetry, free from the turbulent twists that plague other neutron stars. Could nature alone craft such perfection? Some astrophysicists argue yes, pointing to theoretical, supersolid states in neutron star interiors, where quantum effects might lock the core into near-absolute rigidity. Others speculate the pulsar orbits an unseen companion, perhaps a black hole or quark star whose gravitational tides perfectly counteract any rotational wobble, acting like a celestial flywheel. Then there's the wildcard collision history. If two neutron stars merged here long ago, their combined angular momentum might have birthed a spinner so balanced it resists disruption like a gyroscope in zero gravity. But the plot thickens when you examine the pulsar's emission patterns. Buried within its pulses are harmonic overtones, mathematical echoes that mirror the vibrational modes of a perfectly tuned bell. These harmonics repeat at intervals matching prime numbers, a pattern seen nowhere else in nature but frequently in human-engineered systems. It's this detail that fuels speculation about the clockwork pulsar being more than a natural wonder. Could its precision hint at calibration? On Earth, we adjust machinery to eliminate variance. What if some cosmic equivalent occurred here? The implications stretch beyond curiosity. If such stability can emerge naturally, it could revolutionize navigation for future interstellar travel, offering a galactic GPS more reliable than any human-made system. Conversely, if the pulsar's regularity stems from unknown physics or something else entirely, it might force us to reconsider what's possible in neutron star evolution. For now, the clockwork pulsar ticks on, a silent arbiter of time in a chaotic cosmos, reminding us that even in the vast, turbulent expanse of space, perfection sometimes finds a way. Among the glittering tapestry of NGC 262's stars, one stands apart not by its brilliance, but by its absence. The dark sun is a cosmic paradox, a star that should blaze with light, yet hangs in the void like a cutout in the sky, its presence revealed only by the searing infrared waves it pours into the darkness. Telescopes aimed at its coordinates see nothing in visible wavelengths, as if someone has extinguished a candle at interstellar scales. But switch to infrared and the truth unveils itself, a monstrous heat signature, radiating temperatures rivaling our sun's surface, yet mysteriously shackled from shining as it should. What could silence a star's light without dimming its fury? One explanation ventures into the realm of degenerate matter, exotic states of crushed atoms that defy ordinary physics. Picture a stellar core so dense, its electrons have been pressed into a quantum slurry, absorbing visible photons like a sponge while rerouting energy into longer, invisible infrared waves. Such a star might resemble a husk of crystallized carbon, its outer layers transformed into a cosmic insulator, trapping light beneath a shell of ultra-dense material. Simulations suggest this could occur in stars teetering on the edge of collapse, their internal furnaces faltering just enough to trigger this bizarre metamorphosis. But there's a wilder possibility cloaking, not the sci-fi variety, but a natural phenomenon where the star's own atmosphere bends light away like a cosmic mirage. Imagine a shell of ultra-cool dust and plasma swirling around the star, its particles precisely sized to scatter visible light while allowing infrared to pass. This wouldn't be mere obscuration, it'd be a perfect optical filter engineered by nature. Some astronomers even speculate about gravitational lensing gone rogue, where the star's immense warping of spacetime acts like a lens cap, diverting its own light sideways and leaving only heat to escape. The dark sun's influence on its surroundings deepens the riddle. Planets orbiting it, if any survive, would bask in relentless infrared warmth without ever experiencing daylight. Photosynthesis would fail, yet geothermal energy might thrive, painting a picture of ecosystems built on heat vision and subterranean chemistry. Even more unsettling, the star's infrared jets show faint modulation, pulsing in slow cycles that resemble a heartbeat. Is this the natural rhythm of a dying star, or something else, a signal, a malfunction, or a side effect of physics operating at the edge of comprehension? Whether it's a quantum quirk or a cosmic blind spot, the dark sun forces us to confront the limits of stellar models. It whispers that stars, the universe's most familiar beacons, might hide chapters of their lives in shadows we're only learning to perceive. And as long as it lingers there, dark yet seething, it will keep challenging us to ask, how many other stars are hiding in plain sight, their light turned inward, their stories waiting to be told? In the turbulent heart of NGC 262, nature's fury takes on a surreal new form. The magnetic tornado, a whirling spire of superheated plasma stretching 3 times the height of our solar system. Unlike earthly tornadoes which fade within hours, this colossal vortex has churned non-stop for at least 2 centuries, its spiral arms etched with filaments of ionized gas glowing like neon veins. What makes it extraordinary isn't just its scale, but its defiance. The tornado spins perpendicular to the galaxy's magnetic field lines, carving its own path through space as if the laws of electromagnetism are mere suggestions. At its core lies a puzzle physicists can't quite unravel. Plasma tornadoes should be fleeting without containment. Their charged particles dissipate in seconds. Yet this one maintains its structure with eerie precision, its billion-degree strands twisting in perfect helical formations. Spectrographs reveal why. The tornado isn't just shaped by magnetic fields, it generates them. As the plasma spirals, it acts like a dynamo, amplifying weak galactic fields into a self-sustaining feedback loop. Picture a river that not only follows the landscape but sculpts its own canyon as it flows. That's the level of recursive control this phenomenon exerts over its environment. The energy source is even stranger. Most cosmic plasma structures draw power from nearby stars or black holes, but the magnetic tornado thrives in isolation. The key might lie in its rotation speed faster than any known natural plasma vortex, approaching 1% of light speed at its tips. This creates a relativistic pinch effect where the plasma's own inertia squeezes it tighter, releasing stored energy like a coiled spring. Some researchers compare it to a nuclear fusion reactor without walls, where the tornado's twist confines and heats the plasma autonomously. Then there's the stability. Normally, such extreme velocities would tear a structure apart, but the tornado's strands are braided like cosmic rope, with magnetic knots forming at regular intervals. These act as shock absorbers, redistributing stress and preventing unraveling. It's a design engineers might envy, a self-repairing, energy-generating plasma filament that could, in theory, persist for millennia. What truly captivates scientists, though, are the tornado's eyes, calm, circular voids spaced along its length where the plasma goes eerily still. These zones emit low-frequency radio waves that pulse in sync with the galaxy's rotation, hinting at a deeper connection to NGC 262's core. Could the tornado be a cosmic siphon funneling energy from the galactic center? Or is it a sign of something more profound, a visible thread in the universe's invisible magnetic web, revealing forces that bind galaxies in ways we're only beginning to grasp? As long as it spins, the magnetic tornado will remain both a marvel and a challenge, a reminder that even in the coldest depths of space, nature's most violent dances can hide breathtaking order. And somewhere in its glowing spiral lies a secret: how chaos and magnetism can conspire to build a storm that outlasts empires. Orbiting a forgotten gas giant in NGC 262, the ghostly ring hangs in space like a phantom's halo, a planetary ring system that flickers in and out of visibility depending on how you look at it. To the naked eye, or even through standard optical telescopes, this vast cosmic band appears utterly empty, a void where other gas giants proudly display their icy adornments. But switch to ultraviolet or certain infrared wavelengths, and the ring materializes in eerie splendor, glowing with spectral signatures that match no known element in our periodic table. It's as if this ring exists half in our reality and half in some other, its particles only occasionally deigning to interact with the light we can see. The composition of these rings is the first jaw-dropping puzzle. Spectrographic analysis reveals narrow emission lines that don't align with any molecular or atomic transitions catalogued by scientists. Some researchers propose they're made of metamatter, a theoretical form of particles that interact weakly with ordinary photons, absorbing and re-emitting light only at extreme energies. Imagine a fabric woven from threads that vanish when you look straight at them but shimmer when viewed from the corner of your eye. That's the maddening elusiveness of this ring. On Earth, we've synthesized exotic states of matter in particle colliders that last nanoseconds. But here, nature seems to have stabilized the impossible on a scale that dwarfs our solar system. But the weirdness doesn't stop at invisibility. The ring's structure defies orbital mechanics. Instead of a flat, uniform disk, it's braided strands of unknown material twisting around each other like a cosmic DNA helix. These braids pulse rhythmically, tightening and loosening in cycles that match the gas giant's magnetic field fluctuations. That suggests an unseen interplay between the planet's magnetosphere and whatever the ring is made of, a dance of forces we've never witnessed elsewhere. Some models hint that the braids might be topological defects in spacetime itself, remnants from an era when the universe's fundamental forces hadn't fully separated. If true, the ring isn't just an orbital feature, it's a fossil, a relic of cosmic symmetry breaking frozen in time. Then there's the dimensional overlap theory. Quantum physics allows for the existence of higher dimensions curled into scales too tiny to detect. Could the ghostly ring be a place where these extra dimensions leak, its particles oscillating between our reality and others? Supporters of this idea point to the ring's occasional gravitational lensing effects, moments when background starlight bends around it in ways that suggest more mass than visible matter should account for. It's as if the ring contains hidden folds, pockets where gravity spills over from dimensions we can't perceive. The most haunting detail, though, is the ring's silence. Most planetary rings emit faint radio waves as charged particles collide, but this one is eerily mute except for one recorded incident 7 years ago, when a burst of ultra-low-frequency vibrations echoed across the galaxy. Lasting just under 3 minutes, the signal's waveform matched no known natural process. Some astronomers called it a ringquake, a structural adjustment in the braids. Others dared to wonder, was it a greeting, Whatever the truth, the ghostly ring forces us to confront how much we still don't understand about the basic ingredients of reality. Whether it's made of metamatter, dimensional scars, or something even stranger, one thing's clear: this isn't just a ring. It's a ripple in the fabric of the known, a whisper from the edges of physics, and a reminder that the universe is always ready to surprise us with specters where we least expect them. Amidst the swirling chaos of NGC 262, a world hums literally. The resonant planet isn't just geologically active or storm-ridden. Its entire atmosphere throbs with a singular, unchanging tone, a deep bass note that reverberates through space like the heartbeat of a sleeping giant. Imagine standing on its surface, not feeling wind but sound, a pressure wave so constant it would shake your bones. Telescopes first detected this phenomenon as rhythmic distortions in starlight passing through its air, the kind of regularity that makes astrophysicists double-check their instruments. Planets aren't supposed to sing, yet this one does, unwavering, as if tuned to some cosmic tuning fork. The secret lies in the planet's brutal marriage of forces. Locked in a close orbit with a pair of neutron stars, its crust and skies are stretched by gravitational tides so extreme, they make our moon's pull on Earth's oceans look like a gentle ripple. Every pass of its stellar companion sends shockwaves through the planet's molten mantle, forcing plumes of superheated gas up through volcanic pipes that act like gigantic organ tubes. These eruptions aren't random, they're timed. The neutron stars' orbits are so precise, their tidal squeezes hit the same subterranean chambers at identical intervals, turning the planet into a colossal wind instrument. Each blast of gas through these volcanic vents reinforces the atmospheric oscillation, creating a feedback loop that sustains the tone. But here's where it gets stranger. The planet's atmosphere isn't just vibrating, it's filtering. Spectral analysis reveals its cloud layers are arranged in stacked bands of different densities, a natural soundboard that amplifies the fundamental frequency while dampening harmonics. This isn't noise, it's music crafted by physics on a planetary scale. The effect is so pronounced, passing spacecraft have recorded electromagnetic echoes in the magnetosphere, where charged particles spiral in time with the atmospheric hum. What defies explanation isn't the resonance itself, but its purity. On Earth, even the most stable natural vibrations, like the hum of a glacier or the rumble of a volcano, drift slightly over time. Yet this planet's tone hasn't varied by more than a fraction of a hertz in centuries of observation. Some researchers speculate its core might harbor a crystalline structure, perhaps a matrix of ultra-dense minerals like post-perovskite, whose rigidity acts like a metronome for the entire world. Others propose the neutron star's magnetic fields are somehow entrained with the planet's own, creating a synchronized system where gravity and magnetism conspire to lock the rhythm in place. The implications ripple far beyond curiosity. If such resonant planets are common, they could serve as natural gravitational wave detectors, their tones shifting subtly as space-time ripples pass through them. There's even a tantalizing possibility that advanced civilizations might use them as communication beacons, a theory bolstered by the fact that the planet's frequency falls within the range some astrobiologists consider optimal for interstellar signaling. Whether it's a geological oddity or something more profound, the resonant planet stands as a reminder that the universe doesn't just create worlds, it orchestrates them. And somewhere in that endless hum lies a melody we're only beginning to hear. The shrinking nebula defies one of space's most fundamental rules: nothing in the cosmos should vanish this fast. While most nebulae expand gently over millennia or linger as fading remnants, this cloud of gas and dust is collapsing inward like a deflating balloon, its outer edges retreating at nearly 3,000 kilometers per second. That's not just unusual, it's outright illegal under conventional astrophysics. Imagine watching a fireworks display in reverse, every sparkling tendril snapping back to center stage in minutes instead of drifting apart. That's the kind of cosmic whiplash astronomers are witnessing here, and it's rewriting what we thought possible for stellar evolution. What could possibly yank a nebula inward with such violence? The prime suspect is gravitational sabotage, an unseen stellar corpse lurking in the cloud's heart, far denser than anything we've detected. Most planetary nebulae form when aging stars shed their outer layers, leaving behind a white dwarf too faint to dominate the expanding cloud. But spectrographs of the shrinking nebula reveal gravitational tugs stronger than any white dwarf could muster, suggesting something far nastier might be at work. A neutron star or even a small black hole could be hiding in the chaos, its gravity clawing back the nebula's material like a spider reeling in silk. Supporting this, X-ray telescopes have caught flickers of high-energy radiation from the nebula's core, exactly the kind of screams you'd expect as gas spirals into a voracious, invisible predator. Yet there's a twist: the nebula isn't contracting evenly. Its western flank collapses twice as fast as the eastern side, as if being tugged by separate hands. This asymmetry points to an external force, perhaps a nearby magnetar's crushing magnetic field, squeezing the nebula like a cosmic fist. Magnetars pack magnetic fields a quadrillion times stronger than Earth's, capable of distorting matter light years away. If one lies even a few star systems over, its invisible lines of force could be shepherding the nebula's particles into this unnatural implosion. Then there's the dark matter wildcard. Simulations show that if the nebula drifted into a dense knot of dark matter, the extra gravitational drag might accelerate its collapse. Think of it as wading through an unseen current. The nebula's outer layers would slow first, while inner regions keep plunging inward, creating the illusion of a shrinking surface. It's a fringe theory, but the nebula's light shows subtle spectral shifts consistent with matter interacting with something invisible, the most unsettling detail. The shrinkage is accelerating. Last year's measurements showed the nebula losing 10 solar masses per century. This year's data, nearly 15. If this trend continues, within decades we might witness the unthinkable, a nebula vanishing in real time, leaving behind only a cryptic gravity well and a flurry of unanswered questions. Whether it's a hidden monster, a magnetic quirk, or a dark matter anomaly, the shrinking nebula is a masterclass in cosmic impermanence. And as it disappears before our eyes, it's teaching us that even the grandest structures in space can fold faster than we ever dreamed. Deep in the swirling heart of NGC 262, two cosmic titans perform a dance that shouldn't be possible: the binary black hole paradox. These gravitational behemoths, each weighing millions of suns, pirouette around one another in an elegant, eternal waltz, their event horizons separated by a gap so narrow, physics insists they should have collided eons ago. Yet here they are, locked in orbit like stubborn partners refusing to touch, defying every simulation that says such a pairing ought to end in a cataclysmic merger. It's as if the universe itself hit pause on their inevitable doom, leaving astronomers scrambling to rewrite the rules of how black holes interact. What keeps these monsters apart? The first clue lies in their motion. Most black hole binaries spiral inward over time, losing energy through gravitational waves until they collide in a universe-shaking burst. But this pair's orbit remains stable, their separation unchanging, as if propped up by some unseen force. The leading theory points to frame dragging, an effect predicted by Einstein where spinning massive objects literally drag spacetime around with them, like a spinning stone twisting a tablecloth. If both black holes rotate at extreme speeds in opposite directions, their competing spacetime vortices might create a repulsive buffer, a kind of gravitational standoff where neither can gain the upper hand. But there's a catch. Frame dragging alone shouldn't sustain this equilibrium for long. The system ought to decay. That's led researchers to hunt for hidden mediators. Could a disk of ultra-dense dark matter orbit between them, acting as a cosmic shock absorber? Or perhaps a third object, a rogue neutron star or even a primordial black hole, lurks just out of sight, its gravity subtly balancing the duo like a tightrope walker's pole. Some simulations even suggest the black holes might be feeding on opposite sides of the same accretion disk, their jets pushing against each other like celestial sumo wrestlers locked in a stalemate. Then there's the wild card, quantum entanglement. On microscopic scales, entangled particles instantly influence each other regardless of distance. Could some macroscopic version of this phenomenon be at play here, linking the black holes across their event horizons? It's a fringe idea, but the math hints that if information can't escape a black hole, perhaps quantum correlations might persist outside it, creating a subtle bond that resists merger. Imagine two whirlpools in a pond, each spinning in perfect opposition, their chaos cancelling out into eerie stability. The implications ripple far beyond this odd couple. If black holes can resist merging through mechanisms we've yet to grasp, it could explain why supermassive binaries are found in so many galactic cores without evidence of collisions. Perhaps the universe is littered with these stalled duos, their gravitational waves silent, their dances frozen mid-step, and somewhere in their stubborn orbits lies a secret, not just about how black holes interact, but how space-time itself behaves under the most extreme conditions we can imagine. For now, the binary black hole paradox remains a cosmic riddle wrapped in a gravitational enigma. Every observation peels back another layer, revealing how much we still have to learn about the universe's most destructive and most elegant partners. And as long as they keep spinning in defiant harmony, they'll challenge us to rethink not just how black holes collide, but how the fabric of reality weaves itself together in the darkness. At the outer fringes of NGC 262's star system, where the light of its sun grows faint and the void presses in, an astronomical rulebook lies in tatters, thanks to the impossible planet. This rogue world circles its star at a distance so vast, conventional physics insists it shouldn't cling to orbit at all. To put it in perspective, if Earth were this far from our Sun, a single year would last over 15,000 centuries. Yet against all odds, this lone wanderer persists, tracing a slow, deliberate path through the darkness as if gravity itself has made an exception. What makes this planet's existence so baffling isn't just its distance, it's the lack of anything to explain its stability. Normally, planets this far out either spiral away into interstellar space or collapse inward, unless anchored by a dense circumstellar disk or the pull of hidden siblings. Yet telescopes reveal no such scaffolding here. The planet's star is solitary, its debris field long since dissipated. So how does this world defy the odds? One theory points to dark matter, the universe's most elusive architect. If a concentrated knot of this invisible substance orbits alongside the planet, its gravitational tug could act as an unseen tether, counterbalancing the star's weakening pull. Then there's the rogue planet hypothesis. Some astronomers argue this world wasn't born here at all. It might be an interstellar castaway, flung from another system eons ago and captured by NGC 262's star at just the right angle and speed to enter this improbable orbit. Imagine a cosmic game of pinball where a planet ricochets between stars until one finally traps it in a gravitational featherbed. Supporting this, spectroscopic analysis suggests the planet's atmosphere contains isotopes rarely found in situ chemical fingerprints, hinting at a violent past far from its current home. But the most tantalizing possibility, we're witnessing a planetary mirage. Certain exotic states of matter, like ultra-dense quark clusters or Bose-Einstein condensates, could theoretically form planet-sized objects with gravitational signatures that mimic conventional worlds. If this planet is actually a collapsed fragment of a failed star or a primordial relic from the Big Bang, its orbit might not obey the rules we're used to. It'd be less a planet and more a cosmic imposter, wearing the mask of a world while playing by physics we've yet to fully understand. Whatever the truth, the impossible planet forces us to confront the gaps in our celestial mechanics. Every silent lap it completes is a challenge, A dare to reconsider what we know about how systems form, how orbits stabilize, and how many other outliers might be hiding in the depths of space, laughing in the face of our textbooks. And as long as it keeps tracing its defiant path, it'll remind us that the universe has a habit of reserving its most baffling exceptions for those willing to look beyond the edges of the expected. From the Phantom Nebula's ghostly flicker to the quantum star's entangled heartbeat, NGC 262 isn't just a galaxy, it's a cosmic hall of mirrors, reflecting back every assumption we've ever made about the universe and warping it into something stranger. These 30 objects aren't merely outliers, they're rebellions against the textbooks, each one a crack in the facade of what we call known. Take the frozen supernova defying time's arrow, or the hollow planet, a world turned inside out by forces we can't begin to fathom. Even gravity itself bends to the galaxy's will, with the gravity well anomaly flipping the script on one of physics' most fundamental laws. What ties these enigmas together isn't just their strangeness, it's their audacity. The universe, it seems, delights in leaving breadcrumbs that lead off the map. The dancing galaxies mock our models of orbital mechanics, while the echoing void whispers back in distorted code, as if space-time itself has learned to talk. And let's not forget the bioluminescent cloud, a structure that blurs the line between cosmic phenomenon and something almost alive. Every discovery here forces us to ask how much of our science is just guesswork waiting to be overturned. Yet for all we've uncovered, NGC 262 is just one thread in the tapestry. If this single galaxy can harbor so many paradoxes, what else lies hidden in the uncharted depths of the cosmos? Are there black holes that rewrite their own rules, nebulae that think, stars that sing in harmonies we've yet to hear? The more we learn, the clearer it becomes we've barely scratched the surface. So, what's your cosmic white whale? Which of these 30 mysteries keeps you staring at the night sky, wondering what else is out there? Drop your thoughts below, hit subscribe, and let's keep unraveling the universe's greatest puzzles, one strange object at a time. Because if there's one thing NGC 262 has taught us, it's this: the universe's weirdest secrets are still waiting to be found. Where